Hello and welcome to another episode of the Oxford MAT Livestream. My name's James and today, sequences and series. It's the last of a series of 8 revision sessions where we slowly work our way through the MAT syllabus up there at the top, broken it down into 8 parts, and we're working our way through learning maths along the way. Hi to people in chat like Gannon and Nav and Jewel, I can see in chat. Let me see if I can get chat on screen very quickly. Yes, maybe. There we go. Chat's on screen. We did it. Technology. Some people have noticed that this week I wrote the solutions in a hurry, and there's more typos than normal. Even more typos than normal, I think I can say. Gosh, I'm talking all weird. I've had quite a busy day, including just now. I had to sprint down the full length of the building, do something down the other end of the building very quickly, and then sprint all the way back down the building again. My heart rate is way up. I'm ready for some maths. Let's go. People in chat like sequences, love sequences. David has a better joke than any joke I've ever put into here. People are a little bit thinking about Nicole's here, Adisha's here, Anonymous says these questions are hard. I think they are tough. People often find these sequences and series stuff hard, especially if you haven't learnt it yet. To be honest, I think this is a topic where we'll see on the syllabus, some things even the year 12 going into year 13 students in England might not have learnt some of this content yet. So you might be learning some new maths. If that's you, if you're learning some new maths, then hey, this is a way to learn maths that I didn't have access to when I was your age, to tune into a live stream and learn about sequences. I guess I was lucky that I had something similar like a maths club after school, but for you maybe this is playing the role of that. Nav says, is the institute that big? And to be honest, no, I'm just not in good shape, Nav, but thanks. And Anonymous wants me to update the flashcards. We have this series of flashcards. They're lovely. I have mine printed out and ready to go. Chat occasionally wants me to write new flashcards, and it's not hard to write a flashcard, right? But it is hard to get it into the set of flashcards that are on the web, like push it everywhere else. Anonymous likes sequences and series. There are questions this week. Gannon, the questions came out a little bit late. I've been fighting a battle to release the questions on time each week, and I released them slightly late this week, and with more typos than normal. Good. Right, let's check how the room's doing. We always like to do a how was your day poll. The options are 1 star up to 5 stars for how's your day been so far. I'm having quite a good day, but busy, and my heart rate's coming down again now, so I can talk at more like a normal speed. People are voting for odd numbers in chat. No, not everyone. There we go. Good. Okay. Almost said prime numbers by mistake, but we're all right. Rosie's here. Rosie was at Unique earlier this week. Really like it that as we do Unique summer schools, people find out about the MAT livestream, and I see you in both places. We did a sort of show of hands last week for how many people were here from Unique. Now there's more people. It's a series of summer schools. Kind of some people who do the same stuff. Tara is bringing the best energy in chat right now. Let's have a wonderful session a wonderful sesh. That sounds awkward if I say it. Wonderful sesh today. Yeah, we got like 200 people. Unique is a summer school for some UK students. We do some maths problems and talk about admissions. The question sheets start counting at 0, which is a bit of a joke, I suppose. The next week's computer science episodes also count from 0, which is also a bit of a joke about sequences, I suppose. Average 3.9, which is lower than it usually is, and look at that chart. Look at that chart. It's a real long tail, I would say, of people voting 3 stars and down. If you're having a middling kind of day, maybe you're worried about A-level results, or maybe the weather's been good before and now the weather's not so good, or maybe school's out and you're on holidays and you're not really sure what to do, then I hope that the answer is sequences and series, because that's what I've got planned for the next 2 hours. Right, okay. Each week I try to do a segue from the poll to the maths, and each week it's less convincing. Hi Yasmin in chat. Right, good. I can't read all of the comments, and to be honest, don't actually know if I should. It was like half a normal distribution, or maybe like a Poisson kind of thing, but finite. Anyway, never mind. Harriet's going to be cheered up with some maths as well. Good. Question 3 changes every year. We have to set a different question 3 every single year, so it's different every year. In particular, it's not the same as last year's question 3 because everyone's already done that one. Which Cambridge? See, this sort of question is very exciting, but I should not get distracted by which of Cambridge or Oxford produces better research mathematicians in theoretical physics. I think I'm a research mathematician in theoretical physics, or I was at some point. Anyway, are you allowed to use... One more question from chat before I get onto the MAT syllabus or something, because I think it's general. Anonymous at the top asks, are you allowed to use concepts from 1st Maths or Year 13 Maths if you have learnt it, but it isn't on the MAT syllabus? Yes, the questions are often written so that you literally can't. You have to follow the instructions in the question, but in general, if you have some cool maths, then you're allowed to use it provided it's true and provided it's following the instructions in the question. It's very rare that you can actually pull this off, I would say. So if you don't know cool maths, then, well, hey, I hope you find some cool maths at some point. But if you don't know cool maths, then perhaps you could do this. When did these sessions start up again? Lara, we're not taking a break between now and MAT. There is no gap. We're live every Thursday until November, which still sounds mad, however much I say it in my head. We're live every Wednesday, we're live every Thursday until November. Am I a bit dark on the screen in terms of light? Can I turn that light on? That's a bit terrible. Imperial and UCL don't know if you're applying to... They can't be correlated, because if you're applying to Imperial and UCL, they don't know. It's called UCAS invisibility. Do you need MAT for physics at uni? Physics at Oxford have their own test, which is the physics submissions test. You can find out more on the physics website. They've done a few live stream episodes as well. Good. And at some point there'll be some sort of bonus content. There's requests for more flashcards. I do see the flashcard requests. I do notice them every week, and every week I look at my schedule and think, oh my goodness, how do you update cram? Does uni know if you choose them as firm or insurance? Yes, I think so. I think so? Not certain. I think so. Good, right, okay. I've been distracted by a UCAS technicality question, which is, to be honest, part of my day job. And it is past 5 o'clock, so ha ha ha. Let's do something else. Good question. Very good technical question. Okay, which chat has now answered, so that's good. Okay, breathe. Mature students can do the MAT. There's a question in chat about whether mature students can do my maths test, and yeah, if you're applying to Oxford, you can do. If you're applying to Oxford for maths, you can do the MAT. You probably want to register an open test centre. Check the Oxford website to find out details about testing and open test centres. Okay, right. MAT syllabus. Let's go. At the top there it says sequences defined iteratively and by formulae, which is another word for formulas. So we're going to be looking at sequences. I've got several examples today. Defined iteratively means that sort of thing where each is in terms of the previous one, or sometimes the previous two, or you can imagine more complicated setups, I'm sure. But you might see that each term is 3 more than the term before, like that arithmetic sequences that you see at some point, like the even numbers, right? Each one is 2 more than the one before. That's why I'm defining that sequence iteratively. But you might also see sequences defined by formulas, where the nth term of the sequence might be 2 times n. That's another way to define the even numbers. 2 times n gives you this rule. And the nice thing about having a formula is you can jump straight to the nth term, whereas iteratively you might have to work through the previous terms on the way up. Just because one person's asked, if you're new to the live stream and you want any of the resources, so the question sheet that's on screen, these flashcards that people seem so excited about, there's a single website which is here. You can't click on the screen. YouTube doesn't do links on the screen anymore. Back in like 2010. Anyway, never mind. YouTube doesn't do links on the screen anymore, so there's a link in the description. I could talk about 2010's YouTube for way too long. Right, good. Okay, here we go. More questions about technically when you can do MAT. Anyway, okay. Sequences, iteratively and biformally, there's sort of two different, I guess, philosophies or different approaches to how you might define the terms in your sequence. Something I forgot to say out loud is that with an iterative definition, you need a starting point. You need somewhere to start from. So if I just say a sequence where each term is 3 more than the one before, that doesn't uniquely define a sequence, that defines lots of sequences. I need to say more specifically the one that starts 0. Now I'm talking about multiples of 3. Okay, arithmetic and geometric progressions are maybe new content for people today. So unlike the other live streams where I have rushed through the revision material really quickly, I'm aware that today I might be teaching A-level maths. So I'm on my best behaviour, I'm going to do my best to teach you what those words mean, arithmetic and geometric progressions. We're going to talk about their sums, adding together the terms, and we're going to talk about this thing called a convergence criterion for the infinite geometric progressions. Okay, so I think there's a technical difference here, by the way. The question sheet says sequences and series at the top. I looked into this at one point, and I think a sequence is the numbers with commas, like the numbers, or the numbers an equals n squared or something, the numbers in the sequence. Recursive definition, sorry. And the series is what you get when you add them together. Some people make a distinction like that to talk about an arithmetic sequence being the numbers and an arithmetic series being what you get when you add them together. So distinction there. And we don't do, so just to adjust things that are not in the MAT syllabus, there is no Taylor or Maclaurin series up there, there's no binomial expansion for a general exponent or anything difficult like that up there. There's no general kind of convergence criteria, there's no ratio test, or these are sometimes things that people have asked me about. If you've never heard of any of them, that's the point that I'm making. That's okay, obviously. Right, good, okay. Let's go through a bit of revision about sequences first. So I've got an example there at the top of the screen now. It says n squared minus n. That defines the terms of a sequence. The idea is you can plug in different values of n to get the different terms in the sequence. So here we might try to work out the first few terms by plugging in 1 or 2 or 3. And if we do that, I suppose we get 0 and 2 and 6. So I don't know, maybe we've got opinions about what that sequence turns out to be, but hey, we can at least work out the numbers in the sequence. And the second bullet point down there, I've got a definition of what an iterative definition might look like. You tend to have some function f that maybe takes the previous number and applies some function to it to get you to the new value, which might be something like the square of the previous term. I guess it might involve n as well. That's not in my notation up there, but more complicated, it might involve n. In a nice normal arithmetic progression, each term is a constant difference more than the previous one. So f would just be, let's write this down. I'm saying a lot of stuff out loud. Let's go on screen. In an arithmetic, oh my goodness, why am I zoomed out that much? There we go. In an arithmetic sequence, we might define this like this, to say that a n plus 1, this is code for the n plus 1th term, which I might use to mean the next term if I'm thinking about an, is something like an plus d, where this is some sort of constant difference. Chat's back. Quick check. I got chat on. There we go. Hello again, chat. James tries not to mention Taylor series. Challenge failed. Okay. I check. So this would be some function where like my f of x would be x plus d, or even more concretely, for the even numbers, maybe this is like f of x equals x plus 2. And this is some sort of function that gives you a rule for generating the next even number from your previous even number. I might have picked too simple an example. I'm not trying to insult anyone by talking about the even numbers. I'm trying to keep it a simple example. Each one is 2 more than the previous one. Good. deriving these formulae, I don't think there's many formulae that you need to derive, really. I've tried to explain why it's true. Later down this page, there's a bit of explaining why something's true, but I think we're all right. Hopefully so far, if I show you the even numbers, you could derive the rule that each one is 2 more than the one before. It gets more complicated. Right, okay. So we've got some notation down here for what happens when we're adding the terms together. The idea for this notation, by the way, is so this is a capital sigma, which is the Greek letter that corresponds to S for sum, and the idea is that you read the variable over here downstairs. The variable tells you what you're changing with a starting value and an ending value. So if I have something like this, the idea is that I take this function over here, which might be written in brackets or it might not, and I plug in the values 1 up to 100, one at a time, and I add all of those together. So this would be 2 times 1 plus 2 times 2 plus 2 times 3 plus ... plus 2 times 100, which is one of the questions on the page of questions in a minute. But this might be a nice compact way to write down that sum. It's sort of like a for loop. I've seen this explanation on Twitter get some traction. I don't personally think of it as a for loop, but if you like computer coding, then you might like to think of it as a for loop. It's like for k is 1 up to 100 or something, and then you do something like for k is 1 up to 100, you do some sort of addition. Okay, as I say, I don't think of it like a for loop. I don't have a explanation going there along the way. In chat, somebody says, was one of the revision questions wrong? And yes, and it was this one. The version that went live yesterday, I wrote the answers up in a hurry and I misread my own question. I misread my own question and put up an incorrect answer. So, fun times. I answered a different question. I fixed that 5 minutes before going live. So if you go to the website now and download it, it's now correct. But yeah. People in chat discussing for loops. And yeah, then there's a question a little bit about, do you stop when you get to here or when you get to one before? And I know that's really important in computer. Like, is it while less than, or is it while thing is not true, or something? And the thing I remember for maths is that with this notation, you always put the bottom limit number in, and you always put the top limit number in. By the way, occasionally my whiteboard says that I'm losing connection occasionally. I think it's fine for the live stream, but if occasionally I'm losing the internet and it's going down for a second or two, then really sorry about that. Let me know in chat. Oh, look, Nav in chat has put some code. Let's put that on the live stream. There you go, Nav. Take your screenshot now, feed that to your computer if you'd like your computer to work out some sums for you. Good, okay. There is a formula for these, for arithmetic sequences, arithmetic series, sorry. Let's do that now. At the top of the screen, there's a definition for an arithmetic sequence. It's ones where there's a common difference, like these ones. These are the even numbers. Again, sorry, it's my go-to example, it would seem. 246 up to 200. There's a common difference here where in between these numbers, forgetting about the sum for a moment, in between these numbers, I can select text, there we go. In between these numbers, we just add 2 each time. That's our common difference. So this is an example of an arithmetic sequence. Now I've told you the distinction, I'm trying to get it right, and that's making me get it wrong more. Okay. There's a formula. Now, I'm not a big fan of just showing you formulas, especially if you're a bit younger or if you're just interested. Then there's nothing interesting about being told a formula. But because I'm trying to take it a bit slower and I'm trying to do this like I'm teaching you A-level maths, that there is a formula. It's on the screen there for how the sum of these terms works. So it's the first n terms counting from term number 1, term number 2, term number 3, up to, this would be term number 100 of the sequence. So I guess this is like A1, A2, A3, A100, dot, 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 dot. There's this notation for adding those together then. I guess there's this result, if it's an arithmetic sequence, which just once again is one where there's a first term A, next term A plus D, and then the next term you add D again, and so this 100th term will be A plus 99D or something. There's a formula for adding these together. So here this is 100 terms. In general, if you want the first n terms, they sum to, and then the formula is n over 2 times 2a plus n minus 1d. So, challenge there. How are we going to remember this? And there are several ways in chat. Aha! Several ways in chat. There are stories about famous mathematicians like Gauss maybe inventing this on the spot, aged less than 10 or something. But are fun stories that, hey, let's try and understand the formula that's on the screen. In chat I can see n times a plus l divided by 2, which is a different way of thinking about this. Inside here, I suppose this last term is a plus n minus 1d. There are 100 terms, and that one we've added the difference 99 times. That's an example of a fence post error, by the way, or a fence post problem, where you've got 100 terms, so you've added d 99 times, because your 100 terms have 99 gaps. There are 99 commas between terms of, and it's the commas, the gaps, where we add on a d. So the an term is a plus n minus 1d, not a plus nd. Annoying. So some people in chat are suggesting that we remember this as first plus last in the brackets, because it's a plus this thing over here, a plus n minus 1d. If you split apart these a's and you squint a little bit, you can see, aha, that's one copy of a from the first term, and then this expression with an a would be the last term. So maybe that's easier to remember. If you're adding up some consecutive terms in an arithmetic sequence, you take the first, the last, add them, divide by 2, multiply by the number of terms. Don't forget this n out front. Another way to say that is that the average of the terms multiplied by the number of terms is the sum. Some people like to convert it to the triangle numbers. So if you can remember the formula for triangle numbers, then what you can do is pull out the NA. Let's see if we can do this. Do this live. This is for people who don't want to remember the formula but want to work something out based on easier things that they do remember. Would work like this. The A's are easy to add. There's one A in each term, and there are n terms, so that'll be NA. The D terms are a bit harder to add. They go, there's a D times 1, 2, 3 up to, I guess that's n minus 1. If n is 100, I guess. But that's the triangle numbers. So then you remember that this is n times n minus 1 over 2. So if you can remember the formula for triangle numbers, you can remember that this bracket simplifies nicely. So I'm not sure anybody remembers this formula in their head, NA plus D n minus 1 over 2. But maybe it's, if you remember how triangle numbers work, then you can just use that. You can just use that memory. The sum is the average multiplied by the number of terms, which sounds stupid if you think about it too much, right? Because the average is the sum divided by the number of terms, because of course it is. The trick is that you can see what the average is. The first and last terms balance out in around the average in the same way that the second and 99th terms balance out around the average. Arithmetic sequences are really balanced because they grow steadily, so it all works out. So it's sort of a stupid observation, the average times the number of terms is the sum of the terms, because that's just a rearrangement of the fact about what the average is. The way that's useful is that for an arithmetic sequence, you can sort of see what the average is. It's just the average of any pair of terms equidistant from the start and the end. Maybe that is clever. I don't really know. Okay, do you need the proof for this? I don't think it hurts you to know the proof of this. Here's a proof, by the way, if you know the triangle numbers. I don't think it hurts. I'm not sure you can possibly forget it now that it's on the screen, but it's not the sort of thing that we would normally test in MAT. So if you're just preparing for MAT, nothing else, then maybe you don't use any of your brain power remembering this stuff on the screen. But if you're just interested, then hey, arithmetic sequences are not that different from the triangle numbers. They're sort of stretched and translated compared to the triangle numbers. What's it like at university? Oh, really good at university. Nothing like this, I'm afraid. At A-level and today, we're only really dealing with two sorts of sequences, and there are infinitely many sorts of sequences. There are so many things that sequences can do. At university, you study in general, what can sequences do? How can they behave? The ones that behave even slightly nicely, can we bound them? Can we make any statements about their behaviour? You study sequences in general, not just these two. That's a bit like knowing the difference between learning loads of right-angled triangle facts, and then at some point you learn things like the sine rule and the cosine rule that are just true for all triangles, and that's just much better. Here we're learning a couple of special sequences that behave very nicely, and then later we learn just facts about all sequences. And a couple of questions that are going round and round in chat that I'll do now just to get them out of the way. Question 3 is not planned to change in any meaningful sense. It's still question 3. It's still using the same syllabus that it's always been using for the MAT. We're not planning to make it into a computer science question just because some computer scientists are doing it. And anyway, computer science questions were also based on the MAT syllabus. Same syllabus for question 3, don't worry about it. And the other question that's going round and round in chat is, oh no, is it going round and round, or is it just, am I sorting incorrectly? No, my thing's just crashed. Sorry, I thought those questions kept going back, but actually my chat thing's just crashed. Good times. Okay. We're going to go to the other sort of sequence next, I think, which is on screen now. There we go. That fits slightly nicely. It doesn't quite fit there. Okay. So arithmetic sequence, we just saw where you add the same term each time. The other sort of sequence that you need to know about is a geometric sequence, where the idea is that you multiply by a common ratio every time, usually called R for ratio, but you go like this, so that the nth term is a times r to the n minus 1, or if you prefer to do things iteratively, a n plus 1 is r times a n. So again, there's an iterative definition, I suppose, together with a0 equals a1 equals a. Iterative definition, and there's a formula for these terms. Maybe it is nicer to start counting from 0, you know? Makes everything out by 1 in a different direction. As of this year, CS candidates doing question 3. More information on the MAT website, don't worry about it too much. Okay. Good. Is this useful for investing? Geometric series are extremely relevant. I'm not sure I'd go as far as useful, but hey, if you're paid 5% interest, then your amount of money grows like this. Money 5% more, and then the 5% you need to multiply by 1.05 twice. So you have your cash money multiplied by 1.05 squared. You get a geometric sequence for how much money you've got. The thing about telling people the difference between sequence and series is now that whenever I say either of those words, I'm double checking. Matt can index from 1 or 0 and get away with them. We'll explain it in the question if we have to. I'm being a bit cheeky there. maybe it was not surprising that we could add up the terms in an arithmetic sequence because they're basically just the triangle numbers, really. But I think it is a bit surprising that we can add up terms in a geometric sequence. There's a trick for this, which is sort of explained on the screen there. I think we should learn the formula, so I'm going to try and write this down, so then that this is the sum of the first n terms. I know it's on screen for you, but I think it's good for me to write it down and talk at the same time. The result is that it's a times 1 minus r to the n over 1 minus r, which I suppose is also equal to r to the n minus 1 over r minus 1 all times a as well. This format is slightly nicer if r is bigger than 1, because then you have a positive thing downstairs. Up to you. And this formula is sort of surprisingly simple. There's a couple of lines of algebra up there to try and justify why this works. But you should maybe be surprised that there is a formula, but it simplifies nicely. That's the sign. That's a sign that geometric sequences are a good idea. Does 1, 1, 1, 1, 1 count in chat? Great question. Great question. And Ben, I think as a joke, has asked, can you use geometric sequences to calculate E? Which I fear may be a sort of maths joke. Anyway, yeah, so I would count 1, 1, 1, 1, 1 is a geometric sequence. It's got first term 1 and common ratio 1. I would also count it as an example of an arithmetic sequence. With first term 1 and common difference 0. Question follow-up, is it the only such sequence that is both a geometric sequence and an arithmetic sequence? Answer, no. Please find me another one. Right, good. Okay. Please find me all of them. Okay. That formula for adding the terms together is so nice. It comes from this algebra on the screen. There's one more thing I need to tell you, which is that sometimes we could ignore this term, r to the n. So kind of side note, which I'll do over on the side over here, when is r to the n really small? There's multiple answers to this, right? So I'm imagining r being a real number, and I'm imagining n being a whole number. I'll let you change both of them if you like. I guess n's a natural number. Yeah, and there's this rule for when this happens. In chat, people are suggesting other sequences. Lara has got one, 0, 0, 0, 0, 0, 0, which is an arithmetic sequence and a geometric sequence with, I guess, as an arithmetic sequence, first term 0, common difference 0. As a geometric sequence, Lara can choose to say that it's first term 0, common ratio 17. Good. Okay. Yeah, okay. So there are several different cases here, actually. In chat, because I left it slightly open-ended, chat suggested a few. Some people are saying when n is very negative. Let's talk. If n is very negative, then you're taking your number and you're raising it to a huge negative power. So like 2 to the minus 100 is tiny. That's correct. It doesn't always work though for all r. Let me show you. 1/2 to the minus 100 is actually the same thing as 2 to the 100, which is huge. So we've got to be a little bit careful. It's not just as simple as big N, little n, very negative, very positive or something. There's something to do with whether your number is bigger than or smaller than 1. Yeah, so in chat people are suggesting that the kind of relevant limit for today is if another way to make this really small is to say that if n is very large and if r is between -1 and 1, not inclusive. It's interesting to think about the other cases. That's the one down on the bottom left there. That's the one that we're going to use in a second. I encourage you to play around with this a little bit. If nothing else, it makes you more comfortable with the ideas about when those powers are large or small. I know we talked about drawing the graph of x to the n a few weeks ago, and people seemed a little bit unhappy about the graph of x to the n for large N, which is a similar sort of question about raising these numbers to big powers. So I encourage you to sort of play around with that. Maybe put things in Desmos, graphing software, maybe put them on your calculator. Yeah, so n being negative is kind of a true answer to my side question. It's sort of not relevant in the world of sequences, because in the world of sequences, n is actually a positive whole number. So I was playing a little bit of a game over there to get you to think a little bit more generally, to explore anything out there. I don't think it's got any relevance to sequences. The thing that people get taught in A-level is that if n is large and positive, oh, I'm slightly off the bottom of the screen, there we go, slightly underneath the credits, and r is between -1 and 1, then the sum is about, ignoring that thing, is about a over 1 minus r, which is just ridiculously nice. It's just so tidy. So that happens if you're adding together a lot of terms of a sort of geometric sequence where the terms get smaller. It's not quite that simple, but because of negative numbers, who knows what's going on there. Good. Okay. Good. It's a little bit like small angle approximations. I guess several things are similar in maths. You've got lots of approximations that are secretly limits, but we haven't taught you limits yet. So at some point you'll learn about limits, and then you have this new language for talking about sequences and series, and you get to talk about this much more formally. People talk about the sum to infinity. So people say that the sum to infinity, and people say the sum to infinity converges if that r is between -1 and 1. So the sum to infinity converges if -1 is less than r is less than 1, which is usually written as absolute value of r is less than 1. It's a little bit of extra tech, I suppose. Yeah, and the rule, so you could interpret this rule as saying sum to infinity converges if this is true, and it converges to a over 1 minus r. There is a massive caveat on this, which is that this is all for a geometric series. See, I can't say anything anymore. For a geometric series. And knowing about series outside of geometric, outside of these ones, geometric ones, is not really something I'd expect people to be able to do at all, really. So at university you learn a lot more about summing to infinity. People in chat, I can see, are talking about 1 over n, 1 over n squared. In general, this condition is not enough. Well, in general, this condition doesn't mean anything, because most sequences don't have a common ratio. So what's r? What are we talking about? I suppose if your sequence, there's a version of this that's true. Let's be careful. There's a version of this. You have to do something about r not actually being defined for your sequence, but there's a version you can do to force a sequence to converge. That's way too technical. I'm dodging around something technical, which I shouldn't say. Okay, right. Too cool. In other words, it's too hard. That's what I like about it, right? It's kind of arbitrarily hard. Whatever you're trying to understand, it always feels like there's more content. Like you're never in danger of running out of stuff. I don't know. I never really got on with learning foreign languages. I'm trying to do it later in life, but learning foreign languages, there's finitely much foreign language that you could sort of learn, and then that's it, I guess. That's a terrible summary of language learning. That in later life I've discovered is not how it works at all. Yeah, so let's put it on screen. Nav's got some opinions in chat. The R value for 1 over n would be something to do with the ratio between the terms. And this kind of goes to, the ratio tends to 1 for both of the sequences that Nav was talking about. Let's not go there. In general, loads of weird stuff. I'm learning Spanish, which is not going extremely well, but I felt it was good for me to be trying to learn something. I thought every week I'm telling people about learning mathematics, and I'm talking about strategies for learning and getting better at doing things. I'm also trying to learn things too. The things I'm learning are all different. You never run out of juice in maths, says Alistair, which is good enough to be on the screen. Okay, let's try some questions. I think there's a request in chat that we look at most of these, which I'm up for. Let's do the vote anyway. And I'm going to really ignore this. I'm going to really ignore this question about complex numbers. Flynn, next week we're doing some computer science episodes. We're looking at questions 6 and 7. It's going to be really good fun. We've got lots of logic problems coming up. Logic problems are just nice. We're going to do that for a couple of weeks. The full schedule of what we're up to is on the MAT Live website. Cool, right. We've got 14 of these to choose from. It's just so tempting, right? To be like, if the value of R was complex with a modulus below 1, would the formula still hold? Yes, correct. I can't resist it. Right, there's a vote in chat for which questions we should attempt live. If you want all of them, I guess you've got to click on 14 things, but you can vote for multiple things. Options in chat. And the revision questions cover the things on the syllabus. I moved the questions around a little bit compared to last year, threw in some extra ones, which I then wrote terrible answers to, which I'm trying to fix. Apparently there's a P minus N when it should be P underscore N for subscript. So that's pretty embarrassing. At the moment people are voting for the last couple of questions, which makes sense. I think those are the hardest ones. Do the terms get rotated as you multiply? See, now we're talking about computer. Now we're talking about complex numbers. Yeah, the terms get rotated as you multiply. It's fine. You add them up, it turns to a complex number, but the complex number is still given by A over 1 minus R. It's just that 1 minus R is now a complex thing. Chat is really keen for me to learn Persian, so that's an interesting development. Good, I'm going to let people vote. Let's have a quick look. How many people are actually voting for things like 1? No, it's good, 30% of people. Good 30% of people are voting for, if I assume that these votes are kind of for everything. Good 20 to 30% down here. Voting for absolutely everything, perhaps. It could be totally different people voting for each of the options. No, that doesn't. There's broad support for most questions. Okay, well I think maybe we'll spend a bit more than 25 minutes on this. I can do the 2008 question I can do quite quickly, and the robot question. The robot question's fun, but only has a little bit of sequences in it. To be honest, neither of the long questions that I picked out from the MAT, neither of the past questions are really about geometric series or sequences in the same way that the revision questions are. Now chat wants me to learn Latin. Now chat wants a poll, so that's pretty bad. Okay, right. Enough voting. I get it. We're going to do. Let's make a note of what's won the voting. 4 and 13, 4 and 5 and 13 and 14, and kind of 12 in there as well, maybe, as the ones that are most popular. So I should definitely try and get to the end. Okay, let's go. Yeah, good, okay. What am I doing? I don't know what I'm doing. I've got to turn that off, and then I've got to go over here, and then it's chat on the screen again. But I want to turn off the chat so that I can see the... Good, right, okay. Good times. Okay, and I don't want to go to the split. Woo! It's been a long day. Right, 5:45, let's do some revision questions. Okay, I think I'm going to have a look at most of them. maybe not so much on question 1 actually. Question 1 gets you to work out some values by plugging in numbers. I said this out loud a little bit. You can just plug in values if you've got a formula. It's great. So I would do like 9 minus 3, I would do 100 minus 10. Then I've asked you for the differences, which involves some algebraic manipulation. The hard bit here, I suppose, is that if you're given something like an is n squared minus n, you need to be reasonably happy writing down statements like a n plus 1 squared is n plus 1, a n plus 1 is n plus 1 squared minus n plus 1, or, it's not in this question. Not in this question, but a n minus 1 would be a n minus 1 squared minus n minus 1. In general, my formula here is that I just, whatever it is, I just write it in that space. So, whether it's k or stick figure or whatever, I just stick it into the formula wherever the n's are. The n's are kind of like a placeholder or like a dummy variable, where it means put the thing in here. Okay, I'm not gonna write that one out, but you can imagine having something pretty complicated down there, where again, just plug it in wherever you saw the stick figure. Okay, loads of minus signs. Yeah, I don't know what I'm doing. Good. Okay. Question 2 wants the sum of an arithmetic sequence. That's a calculation. It's an application of the rule from the revision material. I'm not going to tell you the number. That's mean of me, isn't it? I should tell you the number. I think it's. I think the sum is 176, and the 1000th term is 3001. Although I am absolutely losing confidence on that one. It's been defined as a0 equals 1. Got to read the question very carefully, haven't you? a0 is 1. Good. Okay. Yeah, just like a function. Good comment, Flynn. Thanks. Okay. Question 3 has got a sequence that's another geometric sequence. This one, the terms are getting smaller. We're asked to add them together. That's the formula again. It's a good chance to check that you can apply the formula from before. Not that you understand the formula, just that you can plug in the numbers, right? I get something like 3 over 2 times 1 minus 3 to the minus 11. But I did write up the answers in quite a hurry, so I'm really sorry if that's not the right answer for the sum. The sum to infinity converges because r is between minus 1 and 1, and it's a geometric sequence. So the sum to infinity is just 3 over 2. Okay. You can imagine that being, look, this is really close to 3 over 2. This is tiny. You can add on all the rest of the terms and it just gets closer to 3 over 2. Good, okay. Question in chats, the answer is yes, the MAT is a non-calculator test, which we know when we're writing the questions. For these ones, I think it's slightly a calculator thing. I think people maybe use a calculator sometimes, so I don't worry too much if the numbers are horrible. For the actual MAT, we have to worry a bit about people being able to do the calculations. Okay. Question 4, which quite a few people voted for, is this sequence that looks like this. A0 is 1, A1 is 3 times the previous one plus 1, so that's 4. A2 is 3 times the previous one plus 1 is 13, and then A3 is 3 times the previous one plus 1 is 40. And the question is, can we find A and B such that this sequence is of the form A times 3 to the n plus B? Goodness me, I said that in a terrible order, didn't I? Because the question is actually laid out in this rather odd way to say, here's Bn given by a formula. So An's defined iteratively, Bn's defined by a formula. So let's write out some terms of this one. If I put in 0, 3 to the 0 is 1. If I put in 1, I'll get 3a plus b. If I put in 2, I'll get 9a plus b. If I put in 3, I'll get 27a plus b. Okay. So the question is, can I find a and b that make this work? Just checking I've got the numbers right. Good. Okay. If this works, I would definitely need a plus b to be 1, and I definitely need 3a plus b to be equal to 4, which makes me think that a is 3 over 2 or something, and b is minus 1/2. But that's not enough to know that that works for all of the other examples as well. Does it work for this one over here? 27 over 2, take away 1 over 2 is 26 over 2, which is 13. And over here, 81 over 2, take away 1 over 2 is 80 over 2 is 40. So that works over there as well. The formula that I get, I skipped through solving some equations in the middle there for how that works. The way that works is that now we've got a formula, and we should probably check it if it works in general. I'm a tiny bit distracted. Herb's told me that's the B sequence. Oh yeah, I've started writing A's halfway through. Thanks, Herb. My first line was the A's. My second line was supposed to be B's. Thank you, Herb. Some people in chat know about mathematical induction. What I check, I suppose, so here's the definition of the A's up here. The A's have A0 equals 1, which we already checked is true of the B0s. But it's one of the things we used, one of those circled facts that I've used to find the values of capital A and capital B. Well, it's very annoying doing this out loud with a capital A, a capital B, and lowercase a and lowercase b for the sequences. I guess I should check that this formula works in that equation. Maybe I could have done that in the first place, right? I could say, aha, I want... So I have... Let's move these down. Can you tell I learned how to move equations around recently? So now I'm doing it all the time. We have these two rules. We'd like the A's and the B's to be equal to each other. So we'd like both of these rules to be true at the same time, which I guess means that annoying Herb, sorry, I'm going to change that back to an A to say, can we have both of these at the same time? If they're equal. So if the A's and B's are equal, then it doesn't matter which one I write down. So then I could do something like plug this formula into the iterative thing. On the left over there, that would be a times 3 to the n plus b, because that would an would be the same thing as bn. And over here, this term an minus 1, I should plug in stick figure, no wait, not stick figure, n to the n minus 1. And don't forget the plus 1 outside the brackets over here as well. And this almost looks like it works, right? This says, on the left, a times 3 to the n, on the right, a times 3 to the n, bringing those 3's together. It's just these terms down here that haven't quite worked out, right? On the left, I've got plus b, and on the right, I've got plus 3b plus 1. But that's an equation. I could make that work by setting b to be minus 1/2. So I wouldn't quite say that's proof by induction, but I'd say that you can check that the recurrence relation works by plugging in the formula. The reason I wanted to do that on the screen is to show you another example of this n changing into an n minus 1. We had one of these before in the algebra question sheet where we had some powers of x and a formula in terms of a quadratic for the terms in the sequence. We never tell people whether it's going to be a short question or a long question or both on any particular topic. It's fair game. Any topic could turn up in either of those slots. Proof by induction is this technique where you prove something's true for all the positive whole numbers. Maths club for a moment, let's learn about proof by induction. If you imagine a chain of dominoes, you could prove that all of the dominoes fall over if you prove that the first one falls over, and also you prove that every time a domino falls over, this is like one of those domino runs, every time a domino falls, it knocks the next one down. So then if there's a first one and each one knocks over the next one, they all fall over. This row of dominoes looks like the number line, 1, 2, 3, 4, 5, that you learn about. So it's sometimes a useful mental model for proving things about the natural numbers. You prove it's true for 1 or 0, or 2 if you like. You prove it's true at some starting point, and then you prove that if it's true for some whole number, then it's true for the next one as well. So, yeah, I'm not going to do one now, but hey. If I did this shoddy method in the mat, I would think I did something wrong. James does it all the time. Hey, welcome, here we are. Yeah, so backing up a little bit, sorry. This plug it in kind of method, just go for it, right? If ANs and BNs are equal, then I can chuck the formula into the iterative expression, solve for B. This gives us B, but how do I get A? I haven't used the factor. Remember, the iterative expression over here also comes with the information that A 0 equals 1. We've got some extra information. We have to have that for the iterative method to make any sense. Haven't used that information yet. We can also compare that against the formula on the right. So we get this, and also, so there's an and, this is sort of extra information. A times, so A0 be A times 3 to the 0 plus B, that should be the number 1. So if there's extra information, and that contains A and B as well. And this time the A's don't cancel, so we can rearrange this to tell us something about A. A turns out to be 1 minus B, which is 1 take away negative a half or something, so it's 3 over 2. Okay, how much algebra can we skip on the mat? On the multiple choice questions, you can skip as much algebra as you like and still get the marks because you just get marks for answers. On the longer questions, if it's to show that question, you should show at least some working, which might be algebra steps. Right, okay, good. Rosie's got a great description in chat, which I'm going to put on screen. Let's see if I can get that on screen. Oh wow, I think I've just accidentally outed Rosie, sorry. I've done it now. Rosie switched to anonymous. You posted a lovely explanation and then switched to anonymous. What's going on there? It's like proving a ladder exists. If you step on the first rung and then prove that you're okay, step on the next rung, then you're fine all the way up. Really sorry, I read out your name just before you switched to anonymous. Oops. I didn't know you could do that. Right, okay. On a single column, anyway. Can you use Harry also used simultaneous equations. Sorry, still on that question, which I know there are lots of requests for. Can you use simultaneous equations to compare terms for A and B? Yeah, I think that's fine. That was the things I circled, right? Harriet, back up here. I compared terms up here to find A and B. Oh, up here to find A and B. That's not a proof that it works for all n, of course, because who knows what happens next. In fact, it does work, and the question is written as find values of A and B such that this works, which maybe strongly implies that it exists. Yeah, mathematically, we should probably so we can sleep easily at night. We should probably check that it works for all of the values of n, or at least have some sort of understanding or reason why things seem consistent. Okay, 5 is a total mess, so I think I'm going to skip it. It's about rearranging equations. If you want to see me rearrange some equations, there's something in the solutions document on the MAT website, just to take the kind of simultaneous equations and rearrange them. Okay, 6 and 7 are both testing geometric series facts. Each one is the sum of a geometric sequence. They converge provided that common ratio is between -1 and 1. You should work out what the common ratio is for each of them, being careful with minus signs and being careful with factors of x and 2, but then you'll have some understanding of how that's a geometric sequence and you can apply the fact from before. So 6 and 7 I'm hoping are okay. 7 is a little bit messy because of the factors of -2. You would never normally have to do a formal proof by induction in the maths. If a question explained induction, and then the point of the question was to get to do some induction, then fine, okay. But no, going into the MAT, you're not expected to know how to do proof by induction. But if you're thinking about ladders, then you'll be okay. Okay, what are we doing? Not super excited about 8, I'm afraid. There's some addition to do. Test it for whether you can add on the difference the right number of times. In language, the first term, I guess, means A1, which maybe annoys the computer scientists. I don't really know if computer scientists like to count from 0, so maybe they like to call that the 0th term, or do you still call it the first term, but call it A0? Ugh. It all gets a bit messy. But maybe that's a problem with English language. Excellent question in chat. Do I think that doing past papers and the live stream is enough? Sort of hope so, because otherwise I should put more stuff in the MAT live stream, right? I should at least write you some more notes. If I thought you needed more notes, I would write more notes. If I thought you needed more practice, then I guess, yeah, you could do some practice, but some of that's a bit up to you. Especially with index 0, right? Okay, chat's got strong opinions today. Excellent. I love it when chat comes out swinging for the fences, right? Just super on it. And they've taken the opportunity to shout flashcards again. We're going to take a couple of seconds here. Just all caps. Here is my message. All caps all the time. It's times like this that I remember that doing a live stream about mathematics revision on the internet is a fundamentally quite strange thing to do. So let's keep moving. A suggestion, maybe a serious suggestion, that people want more questions. We can at least do more questions now. 9 is a bit weird, but not in a very exciting way. It's one of these arithmetic sequences we were talking about before, where all of the terms are the same. Or maybe the question is talking about no numbers at all, but I'm not really sure if I should count that or not. And 10 is going backwards. So taking a fact about the sum of the terms, can you deduce a fact about the nth term? It turns out this way around is a fair bit easier, because if you know the sum of the first n terms, you know the sum of the first 1 terms. And if you know the sum of the first 1 terms, you know the first term. And you also now know that some of the first 2 terms, which lets you deduce the second term. And now we're off and away until you work out what's going on there. 11 I made a mess of in the solutions document because I can't count, but I can add, and I think it turns out to be 10100 in decimal. Yeah, it turns out all right in the end. So 100 numbers, they're all even, so it's 2 times triangle numbers, says David in chat. Good. If you really love triangle numbers, then you can go for that. Yeah, constant. Oh, I meant n was constant. Yeah, 10's not very well worded, is it? Sorry about that. Right, okay, let's do a couple down here. People really wanted 13 and 14, so I'm going to try and get to those. Let's quickly talk about 12. 12 is a little bit of a joke that if I gave you an arithmetic sequence and I told you the first and the third, you'd be able to deduce the value of 2 times d for the difference that's been added twice. For a geometric sequence, the thing's been multiplied twice. So given that the first term is 3 and the third term is 27, the middle term, that second term, might be 9, or it might be not minus 9. In both cases, I guess the thing that you know is that a is 3 and ar squared is 27. That implies that r squared is 9, but r might be 3 or minus 3. There are 2 solutions here. So there are 2 sequences that this could be. Both of them share the number 243 over here. So when you're adding them, you either want to add these numbers along the top, or you want to add these numbers along the bottom. And you get different sums. It doesn't happen for arithmetic sequences, it does happen for geometric sequences. Good, okay. I just think it's cute that you get these 2 possibilities, right? Because of how positive numbers have 2 different things that square. Anyway, never mind. It's like that polynomial thing again, like roots of polynomials. Makes me wonder about whether you can do something different where you get like 3 solutions for what the in-between thing is, but I can't really think of how that sequence would work. Arithmetic sequences, you give me the first and third terms, I can tell you the second. Geometric, you give me the first and the third, I can tell you 2 possibilities for the second term. Is there a different sort of sequence with enough ambiguity and weirdness going on that telling you the first and third terms gives 3 possibilities for what the second term could be? I don't know if that's interesting or good, but hey, it's in my head, and now it's in your head too. Right, okay. 13's fun. Unlucky for some, that is not a good colour of pen. There we go. Exactly the colour at the top right of the screen. Not what I want at all. I would always work out a few terms. If I'm faced with a totally new sort of sequence, I would always work out a few terms. So this one, the first term is 3. Well, A0 is 3, but I'm calling it the first term, I suppose. And then afterwards, AN is the sum of all previous terms. So it's the sum of everything before. And as you work out a few of these, I think you start to spot a pattern. This is something that at time of recording humans are still better than computers at doing, which is maybe going to go out of date fast, but you're good at spotting patterns in something that's going on. So as soon as I've written 3, 6, 12, 24 on the screen, maybe you're already thinking about what sequence that could be. Okay, the first term is a bit of an outlier. It's a little bit different. But after that, 3, 6, 12, 24 just sings geometric sequence, right? Doubling each time. I can't see why. It's all 3s. Why is it doubling each time? But yeah, it keeps going. Everyone in chat saying complex numbers. No, complex numbers just give you 2 solutions again. You don't get more solutions to quadratics by going to. It's still a quadratic, so you don't get more solutions. You still only get 2 solutions. You need to do something really weird. Suggestion in chat: 3 times 2 to the m. Yeah, I like that. I think I've got that. So then AN is 3 times 2 to the n minus 1 for n bigger than 1 is our guess. I've got that too, I think. Actually proving this is a bit tricky. I would probably use induction, I suppose, if I had to prove this. Which would look something like, if you know that it's 3 times 2 to the power of n minus 1 all the way up to n, then when you want to work out a n plus 1, the next term, what you have is the sum of a geometric sequence. You have all the terms added together, plus don't forget you have A0 as well, and everything just simplifies really nicely. So if it's if A1 is 3, A2 is 3 times 2, A3 is 3 times 2 squared, all the way up to AN is 3 times 2 to the n minus 1, then a n plus 1, the next one, would be the sum of everything that's come before. This is technically strong induction. I really shouldn't be writing questions like this because you definitely don't know strong induction, but hey, it's true for all of them. This is not how ladders work, because for a ladder you just need the previous rung to step up to the next one. So, I don't know, some other sort of apparatus where you need all of the previous ones to work. I don't know, you're building a stack of Jenga blocks. Other brands are available, I'm sure. You're building a stack of blocks and you want it to not fall over because all of the ones before are sturdy and unbroken. You're using all of the things from before. Anyway, if all of these things are true, then I can add them up because this is just a geometric thing inside here, isn't it? I've started saying thing. So then it simplifies really nicely because this sum inside here is 2 to the n minus 1 all over 2 minus 1 is 1. And then even that minus 1 inside the brackets cancels out because this 3 on the front brings it down. Very nice. This simplifies beautifully to 3 times 2 to the n plus 3 times 2 to the n, which is exactly what it should be to be the next thing in the sequence we guessed. That's what induction would look like. Wouldn't do this in the mat. Proving a formula for a sequence is super hard in general. In terms of this revision right here, I would say it's fine to just have a guess as to what the general formula is. In this case, your guess was probably correct. Rigorously, there's some techniques that you could learn to prove those sort of things. I wouldn't expect that kind of rigour in the maths. But I thought you'd like to see some reasons on this stream as well. Do let me know feedback if you want no reasons, just no reasons, just answers. Then the stream could probably be quite a lot quicker if it's no reasoning, just answers. Each time it's equal to its. Hang on, that looks clever. Hang on. I've trained that if anonymous posts something that's like a paragraph, each term is equal to its previous term and the sum of all terms before that. And the sum of the terms before that was the same thing as the previous term, so it's just double the previous term. That's a great reason in anonymous. Right, forget this. People in chat saying they like the reasonings. Anonymous wins this one. That's very good. Yeah. Rewind. So really complicated argument, much better argument. A4, for example, is equal to, I'm going to do an example just to mix it up a little bit. A3, A2, A1, A0, but all of this stuff over here was also A3, because A3 was the sum of the stuff before A3. So this is just 2 times A3, 2 copies of A3 added together, one from literally A3 and one from everything before that. So it's 2 times A3, so it's just doubling. That's a much nicer proof that it's doubling. Well done, anonymous. Sometimes I like to think that anonymous is all the same person, but sometimes I can tell that there's multiple people. Anyway, what was my answer for 13? Yeah, mine doesn't work for n equals 0. Mine is this. An is this for n bigger than or equal to 1. Oh, and special case, it's equal to 3 for n equals 0. I was hoping you wouldn't notice that, because it's a bit ugly, isn't it, to have separate case for n equals 0. I've put brackets around it and everything, like I'm ashamed of it. And this kind of curly brace notation, I'm not really sure when you first see that. Side note again, sorry. Have people seen this, like x for x greater than 0, or for x less than 0? Greater than or equal to, I suppose. You can define these functions sort of piecewise, where you have a piece for x negative and a different piece for x positive, and that gives you a definition which is like a lookup table. It says, give me your value x. Right, first we need to look over here to work out which case we're in. These are called cases. I don't know. It feels super clumsy having that in here, so I was hoping that you wouldn't notice. Right, good. That was really clever from me, brackets, it wasn't me. Well done, anonymous. That's what I was getting at, right? From my point of view, you're all the same person, but from your point of view, maybe you're not. Is it possible to write one including the first term? You can always turn these case-based cases functions into one-liners using some sort of indicator function rubbish, but it's not worth it. Maybe the question should say, oh no, the question does say, hang on a minute, the question does say, find an in terms of n for n bigger than or equal to 1. I already thought of this problem. I just asked for a formula for n bigger than or equal to 1. Already thought of this. Good. Oh, look, David's got some ceiling notation. There you go. There's a one-liner that gets around it. On screen. Now. Something like 3 times ceiling times some sort of rounding up sort of thing. Am I convinced by this? Yes, I am actually convinced by this. Right, okay, good. Rounding up the value of 1/2. Okay. 14, last one, is some calculation. I'll leave the numbers, if you want to get the numbers, they're in the answers. The sequence, if you care, is called Catalan numbers. They're really nice. They should be just as famous as the Fibonacci numbers. They're a bit unloved at kind of school level. They turn up in lots of computer science problems. They're just really good counting numbers. There's a big set of problems to which the answer is Catalan numbers, isn't it? And you can see some of those if you search for Catalan numbers. My handwriting's terrible, so I'm going to write that out again in capitals. I'll lean into the thing chat's doing when chat gets excited about something. Just put a capital letter. Oh, someone said, good job, James. That's what we need. Right, okay. 14, these are the Catalan numbers. I'm not going to work them out live on stream. I'll get them wrong and it'll be embarrassing. Yeah. Oh, let's point let's put it the learning moment in here. There's something slightly odd going on and again, this is a little bit too technical for maths to dig into this too much. But if you want to put n equals 0 into this formula, because you're trying to calculate C1, then you end up with something slightly strange on the right-hand side, which is that your sum starts at 0 and also ends at 0. 0 appears down here and also up here. That means you just put 0 in and stop. Our sums include the lower limit and the bottom limit, and if those are the same thing, our sum's only got one term in it. What have I put in? I put n is 0 or something. N is 0, so I should have replaced that n with a 0 already. And now I'm going to plug in I is 0, so it's just C0, C0, which I should probably write as C0 squared, which is the number 1. Hooray! So the calculation feels a little bit wonky there because the sum starts and ends at the same place. You don't often see sums with numbers at the bottom and the top being the same because your sum's only got one term in. Why would you write that as a sum? Nobody goes around writing like the sum is from I is 1 to 1 of 3 to mean the number 3. Nobody does that. That's just 3. You've only got one term and it's 3. Anyway, okay. Okay, that's I think the learning number. Catalan numbers turned into a non-maths related fiction book. They are in Pascal's triangle. Yeah. If you start, let's not do Pascal's triangle right now. I do Pascal's triangle too often. Okay, short breather. Yes, they start 1-1. Short breather. That I've also interrupted the word breather to write out some Catalan numbers. We're going to try a math question. It's just down here. For people who are new to the show, this is an actual live past math question. It was used in the past, in 2008. It was presented like this. For the MAT Livestream, we've got some hints to help bridge the gap between maybe where you currently are and confidently answering math questions without any hints. On the next page, if you want to look on the next page, there are some hints for each part of the question. So laid out in the same way. I for these different parts of the question. They're supposed to be helpful but not give the game away. Okay. No pressure, Pascal's triangle again. Always Pascal's triangle. It's not PTSD, Flynn. I love Pascal's triangle. The thing that happened in season 6 was they talked about it so much. Okay. I think everyone else got fed up with Pascal's triangle, but I'm still going. Right, okay. That's quite nice. I can fit the question on the screen. I think I want to do bits of this question out loud. We have a second person who's read the book with Catalan numbers in it. So now we've got two people trying to remember what the book is so that we can do book recommendations. That's just really good. They're really good. Okay. How do I want to play this? So, I think I want to talk through the question because this is one of those questions where there's an idea throughout the question. So I think I want to point at that, and then perhaps we'll jump in and do a couple of bits of algebra in the question. The question works like this. We're asked to come up with some numbers at the top that work in a formula. Then we do some algebra. It's got A's and B's in there. It's got a sequence with n's and n+1s in it. And then part 3, we come out of the forest. We've emerged from the algebra. And once again, we're writing down solutions to, that looks like the same equation, right? Thing squared minus 2 times a different thing squared is equal to 1. But now we're asked for massive numbers. We want capital X and capital Y to be bigger than 50. I guess the numbers now are so large that we have to use capital letters to represent them. Chat likes using capital letters for shouting, but here's a sense for numbers so loud you've got to shout about them. And maybe that's a bit surprising as a structure for the question. At the top, we're asked to come up with a solution to this equation. We're going to pick small numbers, right? But then further down, we somehow magically now know how to write down large number solutions to this equation. That's pretty odd. And the secret lies in the algebra on the way through. The question's also got a part 4 at the end, which I'm not ignoring, but in part 4 at the end, it's sort of tagged on as this extra idea about what's going on. Okay, I'm distracted by chat trying to work out what this book is. I'm very invested now. Okay, so if I'm doing this question out loud, I'll probably talk about finding some solutions at the top. I think part 2 is a bit that I'll do on the board, where I'll do some algebra and we'll talk, trying to get some understanding about how these sequences work together. What's going on, right? What's going on in part 2? Maybe you can already see that the thing we're proving in part 2, find positive values in A such that statement, really wide, maybe you can see how that's related to the equation that turns up in question 1 and in question 3. Sorry, part 1 and part 3. Maybe you can see the relationship. And if you can see that relationship, then congratulations. That's the hard bit of this question. The algebra is pretty straightforward. The guessing numbers part of it is pretty straightforward. And once you've had the idea about what's going on, it all links together quite nicely. So I'm going to give the game away in a little bit. If you'd like a hint, there's one on this worksheet. It's on the next page, so I can't quite scroll down and show you the hint. But the hint for part 3 is a sort of quite chunky bit of hinting where I'm trying to get you to have the idea. Okay, so choice. If you keep watching, I'm going to spoil what's going on. If you don't want to know, then you might need to look away from the live stream. Tune back in about 15 minutes. Okay, let's start by doing part 1 together. Can I have some suggestions in chat, please, for numbers that work for x1 and y1? And if you're playing along at home without access to chat, then just, I guess, write the numbers down on a bit of paper or something. I was going to say post them to me, but don't post me the numbers. I don't need the numbers. Right, good, okay. Chat is now going for it, and we're getting proper chat engagement where we're really getting those numbers working. People are saying 3 and 2 pretty unanimously, which is pretty nice, actually. Yeah, so the 3 and 2 is a good one. And now, after a bit of a pause, people in chat are saying 1 and 0, which I also like. I don't know whether the marking team for this question back in 2008 considered 0 to be a positive number. That's, I think, related to how they define natural numbers. But look, if I think 0 is positive, then I'll accept 1, 0. 1 and 0 as a solution. I think 3 and 2 is fine. Have people got any other things? Oh, -3 and -2. Yes, sure, okay. That one, so -3 and -2, I'm really going to say maybe not positive. Yeah, okay, so people in chat seem to also think 0 is not positive, so I shouldn't allow it. Okay. The weird thing is, nothing goes wrong. You get to do the rest of the question just fine. So it feels a bit harsh to punish people for writing down 1, 0. 1, 0 kind of is the starting point of what's going on here. But hey, it says positive integers. So I agree. The question says positive integers, and 0 is not really a positive number. But in what follows, kind of nothing goes wrong. We're going to see that we're going to generate new solutions with bigger numbers. Okay, part 2, I think that's pretty clearly an algebra bash. Sort of try some algebra and just go for it. I'm going to do it on the screen. If you want to try it at home, you can probably do it faster than me at home. So if you've still got that bit of paper where you wrote down the numbers 3 and 2, you might like to try writing out the algebra. It'll at least be interesting to you, I think, to see if you're doing the same sort of algebra as me. And now the challenge for me is to do the algebra. Okay, so here's what we've got. We have several things. We have xn plus 1 is equal to 3xn plus 4yn, oops, and yn plus 1 is equal to axn plus byn, and we want something pretty messy to happen. Xn plus 1 squared plus, minus 2 times yn plus 1 squared to be equal to xn squared minus 2yn squared. Presumably we want this to be true for all n, I think. And the question says that we're looking for positive A and B, but here we go. Oh, Mars has plugged it in with actual numbers. That seems kind of clever, I like that. So if you plug in numbers, you can try and make it so that A and B work. Oh, Leo has been told that 0 is both positive and negative, which I guess is a different way to split the conundrum. I think my strat, maybe this is what you're already doing on your bit of paper, way ahead of me. My strat is to sort of plug things in and see if it works. So we would need 3xn plus 4yn squared take away 2 times axn plus byn squared to be equal to xn squared minus 2yn squared. Miles in chat, have you plugged in some numbers that you have from part 1? And have you calculated yn in n plus 1 in terms of a and b? Is that what's going on? That sounds quite nice. It's not what I thought of. I've got to be really careful multiplying it like that. Like, I hate it when I'm squaring something and one of the terms is even. So you get an even number, and my brain's like 12. Oh, brilliant. I must have remembered to multiply by 2 already because 12 is even. It's like, stupid brain. I need to multiply by 2 again. 16y squared minus 2a squared xn squared minus 2. No, you see, because there's a 2 from the outside, which made me think that I already had the factor of 2 from squaring. Been a long day. I'm now talking to myself about squaring. I'm not talking to myself, I'm talking to you. Mystery people on the internet. Right, okay, this looks really implausible to work. I guess what I want is, it would be nice if the coefficients matched up. I'm using coefficients in quite a loose sense here. The things in front of the xn squareds, it'd be nice if they matched up. I've got all this xn, yn mess on the left. It'd be nice if that just went away. And I've got the yn squared terms as well. It'd be nice if they worked out too. There's a third one in here. So yeah, fair enough. Oh, Mars chats came back in reverse order. Whoops. Yeah, they sometimes get approved backwards. You can make that work. And it works now if you say, this is not totally rigorous, but if you say, let's try having, 9 minus 2a squared equals 1, 24 minus 4ab is equal to 0, 16 minus 2b squared is equal to minus 2. Things turn out okay if you do this, which is why I think it's an okay math question. If this didn't work, then it could maybe still sometimes coincidentally work for special values of xn and yn. Like if, this is not the case, but if xn and yn were both 0, then xn plus 1 and yn plus 1 would both be 0, and then it doesn't matter what the values of a and b are, it's just 0 all over the place. 0 squared, I go 2 times 0 squared, well that's equal to 0 squared minus 2 times 0 squared, doesn't matter what a and b are. So sometimes this equation could be true, even if the coefficients don't match. But I don't expect you to worry about that. I expect you to be basically done solving this because you're way ahead of me, right? Your bit of paper has already got the answer on it, which is like 2 and 3 or something like that. Hey, those are the numbers we had before. That's probably a coincidence, right? With a minus sign, or with a minus sign or something. Yeah, 2 and 3. A is 2 and B is 3. Okay, do I need to follow through and solve for anything else? No, we're good. Okay, we found A and B. That was part 2. Let's look at the question again. And this is the key moment, I think. We now look at the question. We've just done a massive bit of algebra. Maybe algebra makes you tired, or maybe it makes you invigorated for having solved for A and B. You can check your answer. Oh, sorry, you're not mystery people, you're anonymous. Why do they equate the equations with 0, 1 and 2? Oh, I was reading off the right-hand side. On my right-hand side, I've got this thing here, where on the right-hand side of equals, I've got exactly 0 xn yns, I've got 1 xn squared, and I've got minus 2 yn squareds. So I've kind of got complicated thing equals simple thing, which means that my equations look like complicated mess on the left and simple things on the right. But that's what's going on. Oh no, I'm going too fast. Should it be an identity sign if we're comparing coefficients? Perhaps. Perhaps. So I know that algebra was pretty messy. I quite like some messy algebra sometimes. It gives you something to do. I don't particularly care about it in terms of your education today, right? Because plugging in those expressions, squaring everything and comparing is probably good for you as practice for algebra, but it's nothing to do with sequences and it's nothing to do with the big idea in this question. The big idea in this question is coming up in a second, and you can join in with this even if you didn't follow that algebra at all. That's maybe an important thing to know about math questions. You can join in later and still get some marks later on, even if you made a mistake earlier on, or even if you got lost and didn't finish the algebra. Still join in again. Because the idea here is that we'd like big numbers, big X and big Y, that satisfy the equation. And the idea is that we can use part 2 to generate those, to make those. What was the answer? The answer was A equals 2, B equals 3. I skipped solving the equations rigorously, but they're not that complicated. A squared, one of them reads A squared equals 4, and I've been told to take a positive number. And once I've set A equals 2, then it crumbles into dust quite quickly. Whiteboard again? Yeah, sure. Question on screen, and I've got the next bit of question on screen as well, so we can talk about both. Pulled out the bits that depend on xn squared on the left and the right, the xn yn bits, and the yn squares. Just to wrap it up under here, this one says that a squared is 4, so a is pretty clearly 2. This one says that b squared equals 9, so b is 3. And then magically, this one just works out. I haven't really looked at it, but if I plug in 2 and 3, oh, it's all good. It's all good. 24 take away 24 really is 0. That's lucky, isn't it? The thing I'm dancing around here is that, in general, this kind of calculation doesn't work. You can't just... there's something special going on here. Okay, so we can generate some new solutions. Harriet wants to know about marking the questions, which I can do in a minute, I think. Groovy. We can use these rules. So at the top here, we've got a rule for generating the next term. It's an iterative rule. There's a pair of sequences, so that's a bit strange. Generating the next x and y numbers from information about the previous x and y numbers, if you want to think about it like that. I currently know xn and yn. That's okay for me to work out xn plus 1 and yn plus 1. So that's pretty nice. For example, if we have x1 and y1, and I think I do have x1 and y1, x1 is equal to 3 and y1 is equal to 2, then I can generate the next one by using those rules. This says 3 times x1 plus 4 times y1. So 3 times 3 is 9, 4 times 2 is 8, so I should put 17 in here for x2, and now over here for y2. A is 2, so this says 2 times 3, and b is 3, plus 3 times 2, so this is 12. 17 and 12. That's pretty cool. This gives me something generated out of nothing. It's a bit exciting. 51 plus 48 is 99, and y3 over here. 2 times 17 is 34. 3 times 12 is 36. Add those together and you get 70. And these are new solutions, and they also satisfy x squared minus 2y squared is equal to 1, because the equation in part 2, one way to read it is to say that x squared minus 2y squared is the same for n plus 1 variables as it was for the n variables. So it stays the same when you generate these new variables. And if you start at 1, the value of that expression, then it stays at 1. So if you like, the thing that we're proving, and we're proving this in maybe quite a strange way, is that 90 squared minus 2 times 70 squared is the same thing as 17 squared minus 2 times 12 squared is the same thing as 3 squared minus 2 times 2 squared, which is 1. And that's true. Like, this is 9081 and this is 2 times 4900, which is 9800. So the difference really is 1. It checks out. But this way of generating new solutions is pretty cool. Where is he getting these numbers from? Where's 51 come from? Yeah, good question. So I'm taking, to get x3, I'm going to point with a light blue pen. To get here, to get this 99, the rule is, I'm using over here, I'm using n plus 1, which is this iterative expression, which I'm used to doing for sequences defined iteratively. It says, for x3, what you want is to put n equals 2 over here. So I'm trying to read off 3x2 plus 4y2. And I've got x2 and y2 over here. So I'm working out 3 times x2, 3 times 17 is 51. And I'm working out 4 times y2, 4 times 12 is 48, and then adding them together. So I'm following this rule. And I was trying to do the calculations out loud, but I guess at one point I multiplied 17 by 3 in my head. Sorry about that. It's so cool that these work. If you're not impressed by this at the bottom, then just generate some more. Keep generating them until you are impressed that you've got huge numbers. And the squares, double the square of that one, square of that one, the difference is 1. I think can't fail to eventually be impressed. Even better, the punchline for part 4 is that these numbers, if you've got huge numbers like this, with x and y, huge, then what you can do is divide by y squared. So x squared over y squared, so dividing by y squared, x squared over y squared minus 2 is approximately 0. Because 1 divided by y squared is tiny. I'm talking about dividing by 70 squared here, which means that x over y is approximately equal to the square root of 2. That's really good. So these numbers that we're generating out here, 99 over 70, is approximately root 2, which checks out, it sort of is true. 17 over 12 is another approximation for root 2. 3 over 2 is another approximation for root 2. This is quite bad, but the approximations get better. The more impressed you are with the numbers, the more impressive they are for the approximation. Guessing in part 3 getting you full marks. If you didn't use part 2, if you just guessed the numbers 99 and 70, then yeah, I think you've got to get the marks. I can't see the bottom right. Yeah, that's where my head is, because it's from a video. Cool. Oh, is it 1 over square root 2? Because y is the small one. Whoops! What did I say? Oops. Is xn the big one? I think xn is the big one. Yeah, phew, okay. Oh, you called y, David's talking about y over x, okay, good. They all got 7 over 5. I'm calculating the numbers. Side note for people doing unique. On the summer school that you're at this week, or last week or the week before, we had a different method for approximating root 2 called a continued fraction, and we had a whole lecture on continued fractions. That's the same thing as this. Those fractions are the same as these fractions. Just a little note there for some people who I did a continued fraction session with. Should probably do continued fractions on the live stream at some point. Not this live stream, because they're nothing to do with math, but should probably talk about them at some point, because they're cool. On the Maths Club, I suppose. We have this other project, January to June. It's like this, but less formal, if you can imagine such a thing. Well, we should talk about fun maths. Unique is a summer school, UNIQ. It's a summer school that I've been involved with for a few years now. It's for UK students, and it's 2.5 days in Oxford, and they get 1 hour of continued fractions, which I will probably turn into a Maths Club session at some point. Not now, but probably there'll be a Maths Club session about continued fractions. If you're very keen, you can look up continued fractions. They're very cool. Or you can wait until Maths Club in January, and there'll probably be an episode, because now I've kind of said that it's happening. It's too late for the summer school, I'm afraid. It finished yesterday. You can get 7 over 5. If you use... Okay. Oh, by the way, over here, if you set x0 to be 1 and y0 to be 0, that solution that some people wanted to use, then everything's fine. you generate the 3, 2 solution. So this number, you put out this 3 and A is 2, so then you get the 3, 2 solution. So if you thought that 0 was a positive number, which maybe it is, who knows, and you wrote down 1, 0, then you generated the 3, 2 solution later in the question, and then it's fine. You're just on the same road as everyone else. I like including it in the pattern because, hey, it gives you the 3, 2, 1, right? Like, you don't start at 17, 12, so if you're going to start somewhere, 1, 0. Yep, good. Yeah, x and y are not equal. Okay. Yeah, they look similar, I suppose. They're both big, but they're both huge. Things can be huge in different sizes. Is that helpful? Jupiter and Saturn are both huge, but they're different sizes. Good, cool. Excuse me. What are we doing? Oh, we've got a MAT question about robots. Here it is. Let's have a look at it. Okay, we've got 20 minutes, so we can talk about some of the question. It's loosely related to sequences because these programs come in a sequence. There's a P1 and there's a P0, there's a P2, P3 and so on. There's a sequence towards the end of the question, which is awkward because in order to get there, we've got to do a bit of work along the way. Oh yeah, gosh, there is a P-N in the question on screen. That's very annoying. Just here, there should be a P_N there. That's a terrible typo. It's because minus and underscore are next to each other. Should we speed through? There have sometimes been robots in question 5. I can think of 2 examples of robots in question 5. We're going to speed run the first few bits of this question like some sort of really fast robot. The way it works is this. You start off with program F, and then the rule to generate your new program iteratively is you write down previous one, L, previous one again, R. That makes it about twice as long. It's not quite twice as long. Let's work out how long it is now. I'm going to cut back to whiteboard. I'm going to keep that there, that rule on the screen, right? It says that Pn+1 is equal to, what you do is Pn, L, Pn, R. Where I guess what we really need to know is that we start with just one command, and then when we do the next one, so P1 will be FLFR, it's on the screen at the top there, that's got 4 commands in it, and then P2 will be FLFR, so we do P1, and then L, and then, oops, FLFR, and then R. At this point you don't really need to be thinking about a robot, or thinking about any movement, or geometry of how this thing is moving and turning. It's just a sequence of letters, right? There's more and more letters. Let's work out how many. The length, ln, is like 1, and then it's 4, and then it's 10. And the rule is something like ln+1, the length of ln+1 is, well, it's the length of Pn to start off with, loads of instructions from my robot, and then one more, length ln, and then length ln for this bit here, the whole batch of instructions come through, please do program Pn, and then one more on the right. So overall I think that's 2 times ln plus 2, which is a bit like the one in the revision questions where it was 3an plus 1, except now it's 2 ln plus 2. Quick check, 1 times 2 plus 2 is 4, 4 times 2 is 8, add 2 is 10, so this is consistent with the numbers that I've actually got on screen, so that's good. There's a hint in the question to solve for this by writing, I guess one way to see this is to add 2 to both sides. If you add 2 to both sides, then on the left you've just got the thing plus 2, but on the right you've got, crucially you've got the number 4, which is 2 times 2. So you could bring out a factor of 2, and if you do that correctly, then you get a 2 inside the bracket, not a 4. Maybe going too fast even for me. Oh well, that expression is really nice. It says ln plus 2 gets doubled to give you ln plus 1 plus 2. So the sequence might not be very nice, but if you add 2, the claim is that this is just doubling each time, which, hey, looks reasonable, right? So if I do 2n plus 2, I get 22. But if I double it, oh sorry, no, add 2, oh my goodness, add 2, I get 24 up here. So it looks quite reasonable actually, that if I add 2, this really looks like 3 times 2 to the n or something, or 3 over 2 times 2 to the n, something like that. And in fact, that turns out to be the case. You can take that observation at the bottom of the screen, where it's doubling each time, and say, aha, this is a geometric series. What's the first term? What's the geometric sequence? What's the first term? What's the ratio? The ratio is 2. What's the nth term? Geometric sequences are one of the ones we know about, so being able to write down the nth term from the first term and the ratio. Fair enough. Watch some guy do the last part using matrix transformations. I would not use matrix transformations for the last part. Let's go. Right, okay, we're down here somewhere. What direction is the robot facing after doing the program? Well, it's turned right just as often as it's turned left, so it ends up facing along the x-axis. I want to skip down to drawing some paths. I have a recommendation for this, which is it's very tempting to give this to a computer. The thumbnail for this episode probably reveals that I did give this to a computer. The thumbnail for this episode is what it does for P8. So P8 has got a huge number of movements in, I guess it's roughly 2 to the 8 or something. So PN has got, yeah. So there's quite a lot of motion going on. It's quite a nice thumbnail. What just happened in this question, says an anonymous person. I was working out the length of the programs. You see, these programs get longer each time. It's about twice as long each time, but there's a couple of caveats on that. It's not just 2 to the n. It's something like 3 times 2 to the n divided by 2 plus 2 or something. And I don't really care about that. The observation I want to make is that it's doubling each time. The question walks you through working out the actual length in terms of n. Fair enough, I guess. I want to draw these programs. I want to draw what the robot does. So I've got these 3 programs, which I'll put over here. I want to draw what happens. So P0 is just walk forwards, robot. So it's facing along the x-axis, and it walks forwards. Now it's facing along the x-axis over here. Brilliant stuff. Thrilling. Well done, robot. P1 works like this. Walk forwards, turn left. I'm not going to draw the arrows every time. Turn left, 90 degrees, and then walk forwards. And then turn right, so now it's facing this way, it's ready to go for whatever happens next. That turns out to be important. It means that when it does P2, P2 works by running P1 first, so it draws the picture from before, and then it turns around. At the end of P1, it turns around to be facing along the x-axis, and then the next thing it does, so I've got to here, the next thing it does is to turn left, so now it's facing this way. And now it runs P1 again. So go forwards, left, forwards, and then these right turns at the end mean that it ends up facing forwards again. But so that means that my P2 picture, I was expecting maybe a staircase thing. If you drew a staircase like this, then congratulations, you've drawn P1, P1, R, and you haven't got the L turn in the middle. Folds around. Okay. The question actually wants us to draw P4, so we're going to have to do quite a bit more work. Let's go. I've just realised that my whiteboard has squares on which I should be using. So P2 is this. At the end of P2, it's facing along the positive x direction. And then, deep breath. What happens next? It turns left. So now it's facing up. No longer facing that way, it's facing up. And then it's going to draw a picture like this. Oh gosh, down here somewhere, sorry. It's going to draw a picture like this, but starting over here and facing that way. Which means you go forwards, effectively go left 2. Well, not left, it turns left, walks 2, and then comes back down over here. It does, in the middle of this, it does a little pirouette in the middle. You can't see, but it does a lot of spinning on the spot. The little robot gets a little bit confused in the middle of P3 because it gets to here, finishes a P1, and then it starts getting ready to do a P2 again. It's halfway through P2, so it does some spinning, and then I think it undoes it again. Gosh, it gets a little bit of a flap around here, but then it gets around to the corner like this. P4 is even weirder because remember the robot finishes up facing along the positive x direction. So it goes around, up, down, it's facing forwards, and then it turns left again, so now it's going over here, and it wants to draw this pattern again, facing along this way. So, and I think this is weird, it goes back along the path it just went along, and then draws this pattern that I just drew like that. So I think this is really weird, it comes down and then up again on this bit of graph. I wasn't expecting it to retrace its steps, but I guess the robot spins around so much that it can just turn around on the spot. The thumb was one of these. I skipped some parts of this question. We should give the robot a name. Can we call it? No. It's not mine. We can't name it after me. Does it fractal? It's a bit fractal, isn't it? It's a little bit fractal. We're about to hit the fractal moment. So P4 is pretty good. It's moved, so the origin is over here. It's moved around here. The effect of all of this is it's now facing along the x direction, and it's at the point -4, 0. There's some notation later in the question, brought in towards the end there, where this is referred to as x4, y4, for this kind of sequence of where it ends up. Observation. A different way to get to this displacement would be if the robot merely turned around, walked forwards 4 squares, and then turned around again. Or maybe it walked backwards 4 squares. So a different way to get the same displacement, the same effect of P4, would be to walk backwards 4 squares. Overall displacement. That means that when it does P5, it'll do this complicated pattern of P4. I've zoomed out quite a bit. Let's go. When it does P5, it'll do a copy of this pattern of P4, be facing along the x-axis, and then it'll turn and do it all again. So what that means is it'll turn left and then do another complicated, I kind of don't want to draw it, I'm going to draw it anyway. One of these, I'm getting quite good at drawing this flower, which if I mark in the pink lines is a bit like it walked backwards 4 squares, turned left and walked backwards 4 squares, like a robot walking backwards, down here somewhere. So the actual picture is really complicated and it includes this loopity-loop. But a simpler way to draw it would be to talk about the overall displacement would be 4 squares back, turn around a bit, keep walking backwards, go 4 squares back. And that is really similar if I call walking backwards 4 squares Q or something. Then what I've got now is QL, QR, which is really similar to how P1 was FL, FR, and then it repeats. So the fractal-like nature comes from the fact that P4 is really similar to P0 in terms of the overall effect. And then it wobbles around there, and then it keeps going. Good. We're keen. Chat is called to call the robot Robert, the robot, which I do like. So I think I'm going to stick with that. Rob the robot. The robot? Yeah, just the robot. So those pink lines form a kind of picture, a bit like a P1. Maybe it should be no surprise to you that this was P5. If I run P6, it's absolute nightmare to draw all of these curly blue lines going around. But the pink lines look like this. They look like P2. Wait for it. When we hit P8, something brilliant happens, which is the pink lines themselves loop us back round to this really larger picture that's just like the pictures I was drawing in blue before, but by P8 it all loops around again, and we end up at the point 16, 0. So P8 has x8, y8 equal to 16, 0. That's the one in the thumbnail. It loops all the way around. I've drawn all the detail of it looping around. But if you think about this kind of meta level of displacements every 4, then you get some sort of nicer pattern. After that, P8 is a bit like 16 Fs. Maybe that's easier to think about. the displacement for P8 is the same as if the robot just walked in a straight line forward 16 squares. After that, it walks straight forward in a straight line 16 squares. A simpler robot would just walk straight there. So for P9, you could get your simple robot to just walk straight there, turn left and walk straight up. Robert the robot. There's a kid on YouTube who's called his or kid somewhere who's called his pet moth Mothew. That is lovely. So matrices are good for rotations and things. So if you know about matrices, you might have brought them in, but I don't think you need to in any sense. Okay. So in the hints, I've got this idea about this, like writing down a simple program over there. You can bring in, so you can bring in your simple program around P4, talking about displacements, or you can wait until P8 and bring it in. Around some point in here, you've got some idea about the relationship. Let's spell out the relationship. I've skipped to the kind of good bit here. There's this equation, which is the sequences part of the question, so let's do that. This equation relating xn plus 1, yn plus 1 to xn yn. With this idea that Pn plus 1 is equal to Pn L Pn R. So the idea here is that we need to imagine what the robot's doing just in terms of its displacement, not worrying too much about the details. So for Pn, it goes from 0, 0 to xn, yn, and it's facing along the positive x-axis. Don't really know how to write that, so I'm just going to draw a little robot facing that way. And then it does an L, so this is what happens on Pn. Then it does an L, and now Robert is over here facing along the positive y-axis. And now, really difficult question, what happens if Robert does Pn now? So facing this way. And if you think about it, not with rotation matrices, but if you think about it in terms of just the change from x to y here, anytime that Robert originally would have moved along the x-axis is now motion along the y-axis. And anytime Robert previously would have been displaced along the y-axis, so he's gone from 0, 0, he's done some crazy motion, but he's got up to here. Any displacement along the y-axis will now be displacement along the negative direction x-axis. Which, if I put this together, says he starts at this point, and his displacement as he's moving, he'll go forwards up the y-axis just as much as he previously moved along the x-axis. And he'll go, left a bit maybe, along the negative direction x-axis just as much as he previously moved up the y-axis. So I've got to put a minus y in here, where the minus sign is because he's rotated now, so positive y motion is now negative x motion. And having a picture like this in your mind of how this is rotated around is probably a good idea. Good, okay. Great at this, rubbish at BibMass. Okay, so it's kind of, it is a rotation matrix really, if you want everything to be rotation matrices, but can just break it down as this kind of, for a 90-degree rotation, you and I have some sort of imagination of how that works, right? Okay, so I'm talking mostly to Basil in chat. I'll put it on screen, I guess. Basil says they've seen someone else on YouTube do this question, obsessing over rotation matrices. I don't know who you are. This is not a reaction video. Again, I could talk about 2010's YouTube too much. 2010's YouTube, you could click on the screen to go to places, and 2010's YouTube, you could make reaction videos. It was amazing. Nobody does reaction videos anymore. The format's completely dead. There's no demand for anybody to react to anything anymore. But back in the day, gosh, YouTube. Okay. So mostly I've been responding to Basil saying, I've seen someone do this with rotation matrices, which has annoyed me so much that I've been talking about rotation matrices quite a lot. That kind of hyperfixation is maybe not useful. No, you see, nobody wants any sort of reaction. Nobody would do that. Right, good, okay. Yeah, there's dead format. It's just happened. Some people tried to copyright it at one point, and then I don't think it's happened since then. Right, good. Okay, we're approaching 7 o'clock at an alarming rate. Oh my goodness, where does the time go? That was a revision session, believe it or not, on sequences and series with some sidetracking and comments about complex numbers and Taylor series along the way. Sorry about all of that. If this was how you learnt sequences and series, then gosh, sorry about that. We will get we will there are notes on the notes on the website should provide a slightly more coherent way of looking through this at your own speed, and there are solutions there, sort of proper written out solutions for all of the questions that we've talked about on the live stream today. Is he being sarcastic? Questions like this make me question my maths ability. Maths ability is fluid. You can work on it. I'm not certain that anybody's born with maths ability. I've tried explaining sequences to tiny children and they don't like it. So I don't think you're born with it. I think you work on it and you learn it. So questioning your maths ability probably means, realising you've got to do some more maths. Sorry, always more maths. Next week we've got computer science special, in the sense that we've got some questions that were set by the computer science department, and we'll be back at some point for more math questions that aren't just computer science questions. I really encourage you to join us for the computer science episodes as well. I know they're labelled computer science, and if you don't care about computers, but remember, math's not a calculator test. So somehow these computer scientists are doing something that doesn't use any calculators in the mat. Complicated stuff. Departmental crossover. Someone there asked me if I was going to be doing a thing. What would you be teaching next week? So next week there's no revision notes, we're just going to do some math questions. And in fact, from now on we're going to do math questions. Brain fry, yeah, that's 2 hours. 2 hours. Actually made Miles laugh, I'll take that. Gracias, Juan. And someone said, can students take math after A-levels? You take the math when you apply. So if that's after your A-levels, if you're applying post A-levels, then yeah, sure, you're doing the math after A-levels because that's when you're applying. Everybody does the math in the kind of period of time when they're applying for maths at Oxford. That's the rule. Doesn't matter how old you are. These small children who don't know any sequences, despite my best efforts, if they apply for Oxford, they take them out. Good, okay. I'm reluctant to do the maths, animation versus maths, partly because I think it's a bit too long. You know, my attention span is not amazing, and partly because I think believe it or not, I have some kind of idea that I should vet the content that appears on the live stream. I know the bar is pretty low, but I have some sort of responsibility to vet the content. I hope thinks it's really good. Okay, right. Okay. Maybe we're gonna do this at some point, but not today because I'm gonna go have some dinner. Bye everyone. I made that sound really important, and it's not important at all. See you, Tara. Right, cool. Okay. See you in 166 hours for more maths. Yes, which is a true statement. No, I'm losing the plot. Bye everyone. Definitely supposed to have something to wrap up with. Saw a video about MAT syllabus practice. Couldn't find the worksheet you said there was. On the MAT website somewhere, Jill. It's buried a little bit because it's underneath this now. But somewhere on the MAT website, if you do Control F or find on page syllabus practice, those resources grew into this. So some of the questions are the same. Right, good. Okay, right. In the future, adios. See you. Right, okay, take care. Bye. How do I stop it? There, woo, we did it.